Bonjour. Donc nous allons commencer. Je vais commencer par présenter le jury. Donc en partant de la gauche, Pierre Sens. Non, pardon. J'avais pas vu Paul. Paul Couder, donc chargé de recherche ici à l'INRIA Rennes, co-encadrant de la thèse. Pierre Sens, professeur à l'université de Paris 6. Rapporteur pour la thèse, César Villot, professeur à l'université de Rennes, Michel Banâtre, directeur de recherche à l'INRIA, chez INRIA Rennes, directeur de la thèse, donc Charles Concel, professeur, donc c'est à l'IPB à Bordeaux. Nathalie Mitton, chargée de recherche INRIA au centre de recherche de Lille et rapporteur pour la thèse. Et enfin Jean-Marc Champeil de la société Veolia Propreté. Voilà, donc eh bien Arnab Sina, vous avez 45 minutes pour présenter vos travaux.
Ok. Merci. J'ai présenté en anglais. Mais good morning everyone. Jury members and my dear friends, I will present my thesis work titled Self-Describing Objects with Tangible Data Structures. This thesis work was funded by ANR in the context Project Bin That Things. Okay, so I believe that a talk on pervasive computing is incomplete without the mention of the pioneer Mark Weiser. He believed that the real world is a computer and all the activities taking place in the real world manipulates the information space in the background, and all this happens without any interface, any explicit interface. This is a brief outline of my talk today. I would provide some background of pervasive computing and then move on to RFID, which acts as an enabler of pervasive computing. Then I would describe in details my contributions of tangible data and tangible data structures. Finally, I would conclude and present some perspectives to this thesis work. So in the next few slides, I would illustrate the background of pervasive computing. Implicit computing. This is one of the features of pervasive computing. All the activities that take place in the real world as the users interact with the daily objects manipulates the information space in the background. We can see here in the picture a girl shopping around in the supermarket with a smart cart. As she puts and adds and removes items out of the smart cart, the price is computed automatically and reflected on the screen. Context awareness is another feature of pervasive computing. Here we see in the picture a sensor mounted on a tooth, and it senses and it is aware of what the person is doing. The activities that can be detected by this sensor is eating, drinking, talking, coughing, etc. Here we see an interactive map where it shows the location of the user, and it actuates by presenting interesting places according to the preferences of the user, like museum, restaurants, etc. on this map. These features are reflected in the environment as we use our everyday objects, and they are embedded with intelligence, and they can also communicate among each other. So this is the typical pervasive computing environment that we envision to have in future. As we in our daily traditional interaction with computers, we come across three building blocks: the real world, the information space, and the interaction interface, and they are connected together using technology. But in the pervasive computing paradigm, ideally the interface should disappear, and the sensing and actuation should take place within the interaction of these two building blocks. In a typical pervasive computing application, The environment is deployed with sensors, and they capture the physical activities in the environment. As after the sensors capture all the data, it needs to send this, transmit this data to a remote processing server to process the data and get a higher level context of the activities taking place in the environment. To do this transmission, it needs to communicate. We have long range communication that is deployed for global infrastructures. They are used to access the services which is located remotely. Irrespective of the location, we can access the services. Whereas in the short range, the transmission takes place within our physical environment. This communication is within the bounds of the physical activities where we perform our physical activities, and hence this is interesting in the context of pervasive computing to act as an enabler for pervasive applications. We will shortly see in the next slide how we do that. Short range communication of course provides data transmission. What is more interesting is its short range that happens within our physical space. This short range is leveraged by pervasive applications to perform to provide different kinds of features. The physical activities that we do in our environment can be sensed and localized due to the short range of this communication. There are few technologies which has very short range of few centimeters, and that is leveraged by some pervasive applications to provide features like interacting objects, security, etc. Here in this picture we see two users interacting with their NFC phones to exchange their business cards. The NFC is a short range communication, and it implicitly makes them to touch the objects together, so that they get a real physical feeling that the business cards are exchanged in reality. It is like a handshake where the objects are coming very close, in the distance. Here we see in the example NFC bank card, and it is used for payment. The short distance of this NFC the short distance of this NFC technology makes sure that the distance is very short between the reader and the card, and within the short range of communication there won't be any eavesdropping to listen to the data exchange between these two entities. Among the short range communication technologies, RFID is an interesting technology that we would focus on in the next few slides. RFID provides a way to sense the objects in the physical space. This is interesting in the context of pervasive computing. There are various ranges of RFID technology like HF, UHF, NFC. Based on the technology, they use different frequencies, and the range varies based on these different kinds of based on the frequencies, their range varies. We also have active and passive tags. The passive tag is interesting because it doesn't need a battery for its working, and it is powered by the reader for its working. The active tag is an exception for the RFID tags. It is very rarely used for very specific applications like toll tags for cars on highways. Here in the example we see a user in the warehouse scanning physical objects in the space. Very likely he is using a UHF technology to scan the objects in the space, and the tags, UHF tags put on the objects, are powered by this reader. The UHF has a very long range, and he chooses it specifically to query the objects within a very large area. The cost is also another feature of RFID technology. It is very cheap and it can be easily retrofixed on very trivial objects like a pointer like this, or our clothes, or something which is very dumb and trivial. In the next slide, I would focus on the data architecture for typically followed by RFID systems. Generally, RFIDs contain a identifier that links to the central server where the entire data is stored. Whenever a RFID tag is scanned, it needs to look up this data on the central server. This is a rarely used architecture by RFIDs. They contain some more additional information other than the ID, but in this architecture also it needs to look up on the central server quite often. This is a typical external infrastructure used by pervasive computing applications. We have the activities happening in the physical world over here. The data needs, every time an event or activity happens in this physical space, it needs to be transmitted to this remote processing server, where it is stored, manipulated to get a high level context of what is happening in the environment, in the physical environment, and then it needs to communicate back the actuation that it needs to do in the physical environment. So there are some issues with this kind of infrastructure. Suppose the network which is used to transmit these messages to the processing server is fails. So the activities and services, the services would break in the physical environment. Suppose this remote processing server goes down. It won't be able to process the data, and again the services will fail over here. And scalability is also an important issue for external infrastructures like this. Whenever there is an event, it needs to send the message and report it to the processing server. So when there are huge number of events happening in the physical space, there will be lots of data that needs to be sent to the processing server for getting a higher level context and doing the computation. Having these data processing servers are also sometimes owned by third parties, so there are issues of privacy and interoperability, and these infrastructures also needs to be deployed over the physical space, so that incurs a lot of cost. Maintaining these servers also incurs a lot of cost. I would explain, let's see some real life situations where we have these problems in the next few slides. We are shopping around in the market and putting items in the cart, and every time we drop an item in the cart, it needs to send back a message for reporting and get a message back as actuation. So what if this network fails? What if this server fails? The services in this cart, the computation will stop and the services will also stop. During Christmas time, there will be a lot of users for shopping around. Every time a user puts the item in the cart, a message needs to be sent back and receive a message as actuation. So there will be issues of scalability in these kinds of situations where there is an overload of activities in the physical space. As we all know that data and infrastructure, external infrastructures are very often owned by third parties. So they have a tendency to concentrate large amount of personal data on these external servers. And if we consider the web context, we already have a lot of our web browsing and web activities stored on the servers like Google and Facebook. In the future, if we consider the Internet of Things architecture, they will also tend to get the data of the things that we use in our daily life. So would we like to have the data of all these things we use in our room in the servers? I'm sorry for the untidy room, but in future they might get data of these objects also. It's not only privacy. There could be many third parties and trying to secure their own data, and interoperability is another issue that would come up. They would not want to share their data among each other, and then providing services would be a big problem. Consider, for example, the logistics for logistics. The Amazon company won't want to share their data with DHL probably, due to security, and it's their own data. Availability is another issue for these external infrastructures. When this the remote processing server is not available, the data server is not available, all the services in the physical world will fail. And we know the NABAS tags, all the rabbits are dead now because the external infrastructure is no more available. So we have a challenge with these kind of external infrastructures with issues. We want to support pervasive services that build smart environment based on the local processing and works autonomously without these external infrastructures. In this thesis work, I would present an alternative architecture to provide pervasive computing that performs this pervasive computing in local physical space and autonomously. And in the remaining part of my talk, I would present this architecture. My first contribution would be tangible data structure using simple objects. What is tangible data? It's the objects themselves. As we handle all the physical objects in our daily life, it will be the data that will be manipulated in the computation space automatically. Here we see an example while we shop around with items. The items contain the data along with them, and the total price is updated automatically in the basket within this physical space without having an external infrastructure. This idea is analogical to the abacus, where people had to interact with the physical objects. Tangible data could be any high-level semantic data used to self-describe any physical object. It could be a 1-bit status bit. It could be a bit more descriptive, like properties, contents, information describing that physical object, or even it could link to other data related to that physical object. How do we implement this tangible data? We use RFID tags that are very simple and can be easily affixed to any physical dumb object. It is asymmetric because on the tag side we don't need any processing and no infrastructure, while on the reader side it has the most processing and it provides the power for the tags. There are variants of RFID technology that can be used based on the application we want to serve. It could be from few centimeters to as long as 10 meters. RFIDs usually store identifier in its typical architecture, as I had shown before, but here we use it in a different way to use the memory for our tangible data. The memory is could vary between 1 bit to 64 kilobit to describe the objects and to make them participate in pervasive applications. RFID tags are cheap, and they come in various form factors to be affixed on different kinds of objects. So it is an easy retrofit to put on physical objects. So we have many ingredients for implementing the tangible data, as we see over here. However, there are several challenges to implementing this approach. The limited tag memory space is a limitation to put the tangible data along with the objects. We can trade off the expressivity and description of the objects with the memory usage for these RFID tags. We have seen in the literature that XML is used to store data on RFIDs, but this is not a proper place to write this kind of data, which is very expressive and has lot of overhead. There are some approaches. We have provided some approaches as solutions to this challenge. Data encoding is the first of them. We can reuse the data for each object, right from the manufacturing to its disposal. We can use the descriptions in various places of its lifetime. We can also combine several RFID tags to utilize and get a bigger memory space. We hope that in future this RFID technology will progress. This is a typical system architecture we follow. We have the local processing node with a local computer and a RFID reader. We have the objects on the sensing side that are sensed by this RFID reader. They are affixed with RFID tags, and they contain the tangible data. And the processing, once these objects are scanned by the RFID reader, the processing is done by the local processing node, and the actuation is performed. We have some limited amount of tangible data written on the RFID tags, and we can use the local processing node to store additional information of the domain knowledge for applications we are performing. We had participated in a applied research project to that was to manage waste using pervasive applications. It provided us a scope to validate our approach of tangible data. Our team ACES had worked on the individual smart bin that would work autonomously to process the data and infer on the data. Another INRIA team, FUN from Lille, had worked on the communication between these smart bins on a citywide scale. Veolia provided the waste management domain knowledge for the project, and Etinio assembled the prototype for the project. So we have tangible data affixed along with the smart waste. As the waste are accumulated in the trash bag, the properties of the physical object changes, and the tangible data also propagates. We put high-level semantic data like volume, weight, etc. on these objects, and when the physical property changes, as in trash bag, the total volume is put on this trash bag as label, and it propagates throughout the waste chain until the waste is put in the bins all across the city. This approach avoids putting sensors on the bin. Having approach with sensors involves gathering all the data with all the physical data, and then sending it to a remote processing server, and then getting a higher level context again. So ours is a direct approach where we put the high level semantic data on the objects itself. We had a remote processing station to monitor the waste collection across the city, and to occasionally check for hazards in any bins across the city. Selective sorting is an important process in waste management. It should be performed at the earliest for efficient sorting, and it reduces contamination. It also ensures the quality of commodity elements that are collected through this process. Here we have an example that we had performed. Here we have an experiment that we have performed, and we had shown using a prototype that the smart objects are tagged, and they contain tangible data of the waste of the element with which they are composed, and the percentage is also put along with it. So based on these criteria, it will be accepted or refused by the bin. Here we have a glass bin where it has some criteria, and based on the condition, the glass bottle will be accepted. However, all objects are not as simple, composed of only one element. We have complex objects like monitor made of plastic, glass, and the criteria is also modified accordingly to the things they want to collect, and based on the criteria, this e-waste bin will accept this monitor. Tangible data can be also used to perform context-aware sorting. By context, we mean the contents of the bin and the external environment condition around the bin. We have described categories of smart waste for this application, like battery, aerosol, electronics, etc. This is a description model for describing the category. We have properties of this category under some external condition, and it has some properties that needs to be avoided by this category. We have used embedded computer with the support of OWL ontology to describe the waste domain, and we also leverage on the reasoner that comes along with it to infer the incompatibilities between these categories. Here we have an example where we already have a glass bottle in the bin, and the tangible data says to avoid metal being put along with it in the same bin. And when we have an aerosol container described with the property metal, the bin infers it to be not safe to be put in the bin. In this second situation, we consider the external conditions as well. Here we have a high temperature surrounding the smart bin, and we have an aerosol can already put in the bin. So a battery described with property that it can cause spark in conditions of high temperature would be refused to put in the bin. We can represent the inference among these categories as a graph. We consider each node to be a category, and an edge between any two nodes would be the interaction between these categories. In this example, we have shown the dotted lines to be safe interaction between these two categories, and here the bold line between these two categories are inferred to be unsafe. We have a special category put in the OWL ontology as self-hazardous. It would be detected as hazardous detected hazardous by its own conditions based on the external factors also. We have followed first order logic to represent and infer these make these inferences. This is an application we have realized, and this is an instance situation where there are some items already present in the bin, and we introduce a new item marked as this category in the bin, and it is detected to be unsafe for the bin. Let's see how. We have another category that might cause explosion if this item is introduced, and we have a second item that might cause violent reactions with this new introduced item because the external conditions are high. So it shows all the reasoning along for the already present items in the bin. Here it lists the critical items present in the bin, and here it shows the status of the last item introduced for the bin. In this case, the item last introduced was hazardous for the bin. So summarizing our approach of tangible data for self-describing objects, we have shown that it is autonomous in nature and it has benefits over external infrastructure. We make customized use of tangible data, and ontology is a good fit for RFID as it can express the additional domain knowledge required for the pervasive applications. So this was our first contribution of tangible data using simple objects. We consider only individual objects for this first contribution. However, in our daily life, we come across many objects which are composite in nature. We can take this as analogical to atoms and molecules, as a single object and multiple objects having a combined property. In our daily life, as I said, we come across complex objects made of various parts. For example, we have a bookshelf over here that needs to be arranged in real life alphabetically. We have the parts of this printer, and it needs to be assembled back once it is repaired. We have a chair from IKEA, and we need to assemble it after we have got it from IKEA. And here we have some of the common belongings we carry in our while we are traveling, and these needs to be collected back after the X-ray scan at the airport. So the information on each of these parts can be interpreted for activities and provide pervasive applications. Each information the information on each of the objects form a data structure linked internally. We call it tangible data structure because it is logical as well as physical. The application would determine what data structure we would use, a linked list, a graph, or a tree. So for the bookshelf example, we used a linked list. We can traverse the linked list as we would traverse the books in a bookshelf, and it would help us to arrange the books as we do the sorting in linked list. Here the parts can be represented as a graph structure, and it would help us to assemble it back. We can represent the objects as a connected graph, a regular connected graph, and it would help us to find the missing objects based on the already present ones. And we can use a tree structure to assemble the furniture back. There are some design parameters for selecting a tangible data structure. The tag memory space is the first parameter for it. We consider also the importance of each physical part for deciding on the tangible data structure, and also the application would decide what data structure to use. Here I would illustrate on identifying the missing ones and assistance as an application in the next few slides. So here we have the IKEA furniture problem. We have these parts. The manufacturer wants to verify for the missing parts. We as a customer, after buying the furniture, need to assemble it back. So how do we do it? Here are some plausible structures. We can use a graph structure to verify the missing parts. It would be useful for the manufacturer, but for us the assembly process is not reflected in this graph. So it would be a problem to provide the application for us, but for the manufacturer it is easy to verify the missing parts. If we use a linked list, the steps for the assembly is reflected in this structure, but it would be difficult to identify the missing part, and also if two parts goes missing, the service will break down for the assembly process also, the steps for assembly process also. The solution we provide for this kind of application is a tree structure. As we move across the tree, it would determine whether it will be a assembly or a disassembly process. If we move top down, it would be a disassembly of the physical object. If we move from bottom to up, it would represent the assembly process. We have considered elementary tree as the granular data element for this approach of tree structure. It represents a group of correlated nodes. here are all the elementary trees marked in the tree structure. We have made some assumptions for this tree structure. That is, each leaf of this tree would represent a physical part, a tagged physical part, and each of the internal nodes are virtual for representing a partially assembled object. Each elementary tree in the tree structure would represent an assembly process, and also it contributes to the resiliency of this local partially assembled structure. So first, when we have the tree structure representation of the entire furniture, we need to distribute the entire information across the leaf nodes. Why? Because each of these leaves represents a physical object that is tagged. So the information is, the entire tree information is stored across the leaves in the tagged physical objects, and once that is done, we can use the physical parts and to reassemble it back by reading the data on the RFID tags. Typically, a leaf would contain one data element of elementary tree, or at most it can contain two elementary trees, one to which it belongs, the elementary tree to which it belongs, and the one from above in the tree structure. To compare, these are two approaches. We can do an assembly of few physical parts. One is this way, and it would represent all the objects being assembled in one step, whereas we can represent the steps of the assembly of different parts at various levels. We have some advantages and disadvantages for this. The first one would contain homogeneous information on all the leaves, whereas the second approach, in the second case, it will have mixed information stored on all the leaves. Also, the first approach will provide greater resiliency, as the data of its siblings will be stored on each of these leaves, whereas in the second approach, the resiliency would be lesser than this. So we have to do a trade-off based on the application we want to provide. The good thing of this approach is we can provide both the structures for different objects at various levels of the entire tree structure, based on the importance of physical parts. To compare these two structures, we perform simulation based on the parameter of memory consumption. Because the tag memory space is very limited, and so we wanted to compare and provide a view of these two approaches. The parameter for our comparison was the average number of IDs that are stored on each of the leaves. So this was our result depicted as a graph. The rate of memory consumption was higher for increasing number of children, and if we considered the two cases, for a given number of leaves being constant, the amount of memory consumption decreased as there were higher number of depths. So summarizing our second contribution of tangible data structure, it facilitates us with more amount of memory if we considering the individual tag spaces on all the physical parts. It also uses the different tangible data structures like linked list, graph, or tree, and we have shown applications where we can identify the missing elements and provide assistance of using physical parts. Now I would state the conclusion, and I would conclude my work over here and provide some perspectives to this work. We have used RFID as the enabler of our approach, and currently it is used as currently, though it is used just to store an ID for a centralized server, we have made use of the limited memory space on the RFID tags for our approach. Our challenge was to provide local processing autonomously, and through our contribution of tangible data, we have shown that we could provide pervasive applications autonomously. Currently, it is limited by the RFID memory, but hopefully this RFID technology would improve in future. Our second contribution was tangible data structure. This tangible data structure naturally represents the relational properties of various objects we have shown in the composite objects as in the chair assembly. It reduces the RFID memory limitation that we faced in the first contribution. This approach of tangible data structure also provides enhanced pervasive application and autonomously that we have demonstrated. This was the typical RFID architecture that I had shown in the introduction. They contain an identifier to the central data server, whereas in our approach we have shown that the information is linked internally in the local physical space, and very rarely it would need to look up on the central processing server for the additional data. We have shown advantages over the external infrastructure in terms of availability, scalability, interoperability, cost benefit, and privacy. This is a perspective of the future work of this thesis. Using tangible data, we can query the local physical space. We intend to provide a design tool to design our own tangible data structure for composite objects. This would help a novice user to build their own tangible data structure for their own physical objects. Our approach is not standalone. It can be provided in collaboration with external infrastructures. It can provide complementary services when an external infrastructure is not available. The idea is similar to the hybrid approach in the trend of IBM's edge computing. And thanks for your attention. Thank you.
Bien, merci pour votre présentation. Nous allons passer aux questions. Je vais d'abord donner la parole aux deux rapporteurs et je vais commencer par Nathalie.
Okay. So first of all, I would like to thank you for this clear presentation. I really appreciated it. There was some stuff that was not so clear for me after reading your document, but now it's clear, so thank you.
Thank you.
I would also like to congratulate you for the manuscript, which was very complete. But of course I have some questions.
Okay.
First, it's a more curiosity question about the tangible data term. Was it an existing term or did you introduce it?
No, it's not an existing term.
We
have tangible interface, but tangible data and tangible data structure, it's not there in the current literature.
So you introduced this term.
Yeah.
Okay. Then my question is relative to your first contribution. It's about slide 26.
Okay.
Okay, so if I understood well, you created this graph to highlight the interaction and possible or not possible interaction and to detect the wrong stuff. But from what did you use at the beginning to define, where did you take the category? Because I guess you did not invent them. And did you have a complete exhaustive list? Or,
okay, so this is an instance of, this represents an instance of inference using graph. So the categories, as I have said before, that we can reuse the data. There already exists, and this represents for the waste domain. I have shown this as an instance for the waste domain using the categories. So there already exists the European Union Waste Manual, where the categories already exist. So as I already told that we need to reuse the already existing data, we have reused those categories here to represent the waste.
Okay. And what if this category list change? If you have new category, do you need to make them manually in the graph, or can you automatically?
It needs to be added on the ontology that we use on the Smart Bin. We have an external infrastructure in place already to provide support when there are problems, and also in this case we can use the external infrastructure to update the data.
Okay, but this is done automatically?
It can be provided as a extra service. We haven't yet considered on this, but of course the external infrastructure, the remote processing server, can do this additional information.
Okay, now my question is relative to your second contribution based on slide 31. Okay, so I understand how you draw an edge in the list, in the tree, but not how you define your graph.
This graph? So we have an identifier for each physical object, and additionally we have a list of the identifiers to which it forms an edge. Okay,
so you need something that gives you the connectivity, physical connectivity.
So this object, suppose for this object is marked as with an identifier 1, it would have a list of the identifier of this and this. So in that way it will form an internal link within.
Okay. Your contribution was all these structures or only the trees?
I have used this as I have a paper on this as a representation of with a graph, and I have this paper already accepted and I'll present in Belgium in June.
Okay, but the result that you provided at the end are only regarding the tree.
Yes, I took this use case as the tree structure use case for presenting the results.
And did you compare all this structure?
No, I didn't really compare all these structures.
Okay.
But yeah, it would be interesting to compare based on the memory space it occupies for the RFID tags.
Yeah, because you just mentioned that the application will determine the structure, but
yeah,
I guess that in some case you can have
yeah, that's a good perspective. I agree.
Okay. And then just a last question. You mentioned something about the memory available on tags, that you will use some space that is already on the tag for your tangible data. But have you investigate something with OPC Global, for instance, to really know what field in the tag you can use and how?
Yeah, there are various data banks in the RFID tags that are writable by users.
Okay, so you just consider to take user data available on already
No, we have
standard
implemented
tags?
using the tags.
Mm-hmm.
There are writable data banks on the tags, and we have used the space to write this tangible data.
The APC global tags?
Yeah.
Okay.
Thank you.
Voilà. Thank you. Deuxième rapporteur.
Merci Madame la Présidente. First of all, I would like to congratulate you for the quality of your presentation. It was very clear.
Thank
It was
you.
a nice presentation.
Thank you.
And as I write in my report, I like your work. In fact, you address very hot, timely topics and motivated by real applications. So it's very important.
Thank you.
I like your solution. Like your beans, your solutions are smart. And one thing I like in your solution is you use RFIDs as they don't are supposed to be used.
Yes.
So I like this idea.
Thank you.
So naturally I have some questions. It's the game. My first question is close to Natalie. The first question of Natalie is to the distribution of your architecture. So you distribute your architecture with local checking.
Yes.
And naturally, when you distribute it, you have a cost of distribution, cost of to maintain the information, cost of consistency of different databases you spread in your network. Do you have an idea of?
No, it's not spread on the network. I mean, you are talking of the tangible data or tangible data structure?
No, on the local readers. So you have a local database to check the compatibilities and so on.
Yeah, right.
So you have to maintain all this local database in your architecture. So, but you already
this would be not very frequent changes, as I mentioned already, that we are reusing. I have proposed the reuse of the European Union waste catalog for the waste domain. So these kinds of documents change every 4 or 5 years. It won't change every day. So it will be a one-time process. It won't be like a change that needs to be implemented every day or something.
Okay. So it's what I want to know, the update rate, in fact.
Yeah.
So it's okay. I have another question about how you detect the incompatibilities of your tags. As far as I understand, your check method is very conservative. So you raise an alert when you are sure that you have an incompatibility. So you avoid false positives. I'm not sure I'm clear. Okay. But do you have an idea of impact of false you avoid false negative to detect? But what is the impact of false positive in your architecture? But because I think in RFID you can have a large number of alerts. What is the impact if your application, if you have a high number of alerts?
This is with respect to the smart bin, right?
Yes, or more generally. Do you have an idea of the impact of do you have an evaluation of the rate of false positive or not? Or?
No, this is not really that what I have done. But yeah, of course, if we try to query a large number of tags, there will be misreads and there will be problems. But hopefully, we hope that this technology will improve in future, and it is with the technology that is a challenge for this approach. But hopefully, we feel that this technology will improve. I mean,
because in your
really,
yeah.
I have not done any comparison based on this actually.
Because in your target application in Bean, you have a large number of RFIDs, so the probability to have false positive maybe can be high, I suppose.
No, actually, if we consider one item being thrown at a time, there would be less chances of this false positive. And also, if we consider Yeah, if we consider this kind of architecture where the global data is accumulated, so we
Okay.
would have one tag per
Okay.
trash bag, so there also
Yes.
it gets reduced
Yes.
in a way.
Okay.
But
and
if we try to read many different kinds of tags at a once, of course that's a problem. But yeah, we didn't really consider that situation in my approach of this.
Okay. I have another question concerning, in fact, fault tolerance and security of your approach, because with your graph, you, in fact, each tag has some information about the other tags. So in terms, because you have a link,
Yeah, okay,
you
the tangible
directly
data
code
structure.
the link of your neighbors in the graph. So in terms of security, it seems not to be so good. What is your because one tag has information about the other tags. If you have one corrupted tag, what is the impact in terms of security?
The tags are attached to the, I mean, in terms of security of the physical objects, it's not a problem because we own all the physical objects ourselves. So if we have a link of parts of the chair, we own all the parts ourselves, so it's not a problem in terms of that security.
Okay.
But the data stored on each of the tags
Yeah.
are identifiers, and these objects are related. So the identifiers are relevant only to this set of tags. So it's not a problem of security in that way.
Okay. And what is the impact of failure, crash failure of one tag in this architecture? If you have
Hash error?
crash failure, you have one crash of your tag.
Okay. In that way, we can detect the missing objects, right?
Okay.
So we can tell that either the object is missing, or maybe that object containing the tag is not read properly. Please verify. The application would be able
But
to.
your structure is broken. Your graph is broken when you have a failure. If you have a tree, for instance, if you have a root of your tree which is down.
No, we have the.
You can have. I see you have some redundancy in your thesis, but maybe I missed something.
So if we have a structure like this,
Yes.
Each of the siblings will know their. Each of the leaves will know its siblings. So
Okay.
if one of the siblings is not present, it can tell that this part is missing. So it has the resiliency as well, implicitly.
Yes, air is good, but maybe
Over
there is
here
some
it has lesser resiliency. That's what I had done the comparison. But this kind of structure incorporates the step-by-step physical assembly process. So this is a trade-off that we need to do, that I already stated. And this is a particular part of the tree. So based on the objects we really want to assemble, if we have many small parts, we can use this kind of structure to represent for the small parts, because there are high chances of having missing objects. If we have big objects, that does not need much of assembly instructions. If it needs much of assembly instruction, but if it's not very prone to getting lost, because the object is very big, the part is very big. So in that case, we can use this kind to represent that part of assembly process.
Okay.
So we can mix and match between these two approaches and compose the entire building process.
Okay. And do you try in your simulator? So you have a simulator for to inject some kind of failure on when you have a big tree to inject.
No, I have done this using random graphs.
Yes.
To.
But your random graphs are realistic for application?
Yeah.
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 Okay. And just to be unrealistic.
So I would say how realistic it is. Here we can consider a graph of having 10 children of depth 4.
Okay.
It would be a big graph actually.
Okay. And it's usual to have so big composite of object.
Yeah.
Yeah. Okay. I was surprised, but
it could be. It
I'm
could.
not in the
It could realistically
because
represent
you
assembly
go
process.
for after the second picture.
Mhm.
I see the number of leaves. I was surprised. It's a very big composite object.
Yeah, for this we had less number of leaves because it was very difficult to find the two cases having the same number of leaves. So we compared only the two structures where we had the same number of leaves for these two cases. So that's why we have less data for this graph, and we have more data for this graph.
Okay. Oh, okay. No, I'm done now. Okay. Thank you.
Thank you.
So now, Charles Confet.
Well, thank you for the talk. It was very good. I can see you're conveying your passion for pervasive computing. You seem to be a big fan.
Yes.
Yeah. So I have a few questions. I guess I was surprised that you assumed that you wouldn't have a pervasive network. Because, I mean, if you look at the trends, it's really the fact that we have network everywhere.
It's not the case always, I would say. Suppose you are in a location where you need to pay for the network, or maybe you move into a new apartment and you don't yet have the internet connection and you need to assemble back your chair. So these are the realistic situations where you might not have the infrastructures yet, or
well,
maybe you go on a camping and you need to assemble the chairs.
Right, but most of the population now lives in cities, and so and in cities you usually have network everywhere. Now, but if you didn't have network, then you could have another kind of technology, which is this a technology like the one proposed by Sigfox. Do you know the? I mean, the idea is that you have those small communication chips. Okay, and they use radio frequencies, and you have a few antennas spread on a city, and so that means that you don't. I mean, you have network basically everywhere, and it's low bandwidth network.
Okay.
And this technology is already deployed in France, actually in Europe and in Russia as well. So it's there, it's here, and it's working. So there you have network everywhere.
But you need to pay for that. It doesn't come for free.
It costs almost nothing, right? So what do you do with this? I mean, how does it change your approach?
They might be in future, as we saw in the external infrastructure issues. My approach is more on providing the services without having these third parties getting our personal data. That is another issue for this.
Well, but we have our mail and photos and documents with Google today. I mean, everybody does that, right? So it's already too late for privacy, don't you think?
No, I don't think this is not. I don't really.
I mean, comparing a chair with email and docs.
Consciously, you would not even want to use Facebook and Google wanting to store your personal data.
Well, okay. So I guess the other question I had was regarding the RFID technology. In your document, you kind of jumped very fast on that technology, and you not sure you really evaluate other alternatives, so other options, other technologies, other ways of realizing this. You kind of jump into the RFID technology and you say, okay, this is what we have, and we have to make the best of it. So would you imagine having other technology that you could use rather than RFID?
RFID provides a way to store the data along with the objects. This is really very useful compared to the other technologies. So within the short-range communication technologies, this approach is really a good fit for us.
Well, okay, so somewhere else in your dissertation you talk about QR code
Yeah.
and a smartphone to read that.
Mm-hmm.
So there, I mean, already you have no information or very small, I mean, no information or almost no information.
Yeah, but
stored.
if we take the pervasive computing paradigm, as we interact with our objects, we shouldn't have an we shouldn't have an additional effort to make the objects being detected in the pervasive environment. So RFID tags provide better ingredients for this approach.
Okay,
For
so
QR code, you really need
right.
to scan it and then tell
Yeah.
the processing
Yeah.
computer that I am using this object now, and then maybe the computation is done.
So here's a big disadvantage I see in the RFID is the fact that it's an kind of all or nothing kind of solution. That is, either everything is equipped with RFID tags or nothing works. So, I mean, there's been papers talking about pervasive computing environments, like homes, for instance, where you have RFID tags that are used, and objects are tagged with that, and people try to do things like activity recognition, for instance. But the problem they point out is the fact that if objects are not all tagged with RFID tags, then your host essentially you can't do anything, and in the long run, you can never ensure that everything is going to be tagged with RFID tags. So where do you see the solution there?
RFID is already in the trend, I would say, and it is a benefit in terms, maybe if the data is reused with our approach. As an alternative, we have also considered the QR code for the waste management. I mean, it stores a lesser amount of memory, but it requires additional effort for the user to scan the tag. I mean, it provides a much cheaper alternative than the RFID, of course. But RFID is already in the trend, and I think it will be in the have
QR
more
code
usage in the future.
The QR code certainly changes your paradigm, because you have the smartphone that has computing power and memory, and it has also communication interfaces. So,
but mostly in QR codes, they have a link to some external.
I know, but it's static information though.
Yeah.
It's not dynamic, so you can't write on a QR code. Okay. So, anyways, last question. You didn't talk about programming those applications. How hard is it?
Well, I did use Java for the entire prototyping of all the applications, and it was not that difficult actually.
Do you have a middleware? You have a framework, something that people can leverage in order to write?
It's not out on the domain, but there may be some administrative thing, because we have this project funded by some agencies. So for that Bin That Things project code, I don't think it's not up to me to put it out on the domain.
Yeah.
But for the others, it depends. Michel has a startup, so I don't know. These things have some proprietary issues, and maybe if there are no issues, I can put them out on the domain.
There's an SDK. There's some kind of a development environment that people can use.
For the moment, I prototyped it on a personal basis. I don't really have put them as a framework infrastructure and to provide easy to reuse by others, but that can be done.
So how much expertise does it require then? Let me rephrase my question.
Well, one needs to know just Java programming, that's all.
That's all?
Yeah.
There's no specific interfaces to use that are kind of tricky?
Of course, we have the hardware interfaces since we are using the RFID. Okay. And in the Smart Bin, we are using the OWL ontology. So it requires a bit of expertise if you want to handle the application for Smart Bin. Other than that, these are the only languages I have used for the entire thesis work.
All right. Thank you.
Thank you.
Merci. Je vais donner la parole à César Villot.
Merci, Madame la Présidente. So I would like to thank you for your document first, because when reading it, I learned some elements that I didn't know, and it was very interesting on that point. And also I appreciate the presentation also, which was almost clear. And I'm not so close to the domain, but more on the, of course, on the network aspect. So my question will be more related to those aspects.
Okay.
But before that, I have a question on when you use the tree, for example, for the IKEA use case. Tell me if I'm wrong. It may happen that you have non-deterministic choice. For example, that makes you taking all the weekend to just assembling a simple chair. How do you manage? Does it happen that you have a non-deterministic choice, and how do you proceed when you have this kind of issue?
Based on my experience of the simulations that I have done,
Yeah.
I have generated these random graphs, and then I distributed the tree structure on the leaves using my distribution algorithm, and then again reconstructed it back. The time really matters based on the number of leaves. I have simulated up to trees having 100,000 leaves. If we have a structure of that huge scale, of course it will take time to compute it back and assemble the structure back. But for smaller trees, it's not very time consuming. It is done.
So you didn't face the situation where you have to choose between, you have the same piece that may appear on different level. You don't have this kind of situation.
No.
Okay. So what would be your contribution for the waste management system suffering for scalability, and what will be the network infrastructure that you need to make it deployable, easily deployable? For example, suppose that you want to deploy this in your waste management system. What will be the requirements on the network layer that will make your service very easy to deploy?
We are really considering an autonomous approach, first of all. But in the project, we have considered very lightweight networks like GPRS connection to occasionally send messages that, okay, the system across the city is fine, or an alert in some bin that there is an alert, please attend it. So these messages are very, very less, because we have considered building an autonomous approach.
So you don't need bandwidth. You don't have bandwidth requirements.
It is very lightweight in the network side.
Okay. And I have a last question regarding you have presented the interoperability issues as more on a service layer. That means that you may not be able to have services provided by different providers that may not interoperate. And my question will be on the network layer again. You have certainly several technologies that can be used, as the one that Charles have talked about just before. So what will be the impact of having several technologies on which your solution will be based to get it deployed? Would it be middleware abstraction that helps in hiding these interoperability issues on the network layer?
The interoperability issue that I considered over here is mostly based on the administrative, and so these are owned by the third parties, and they would really want to secure the data to themselves. They won't want to share it. So the aspect that I have focused on this interoperability over here is sharing the data with other parties among themselves, and they would involve negotiations among themselves to share the data to provide the service and benefit of the greater number of people.
And very last question: what would be other use case or other domain applications that your solution that you provide can be used for? Do you have ideas of other, because you provide a solution for waste management? can your solution be applied to another domain? And if you have ideas about what can be...
Yeah, I said, as I demonstrated in the first slide of the smart cart, it can be used to query a physical space like this. We get into the bedroom, we need to do an inventory, and we can just, with a reader, we can scan and we can tell that what's there in the bedroom. If we have a warehouse, and we can get more details without using any network, that what is my inventory. Without using the network, I can tell in a warehouse that the entire inventory in the warehouse. And for the tangible data structure, we come across many objects like this where we have the relations among themselves. So it would be easy for these kind of approaches to implement the tangible data structure for these objects.
Okay, thank you. I'm finished.
Merci. Donc je vais donner la parole à Jean-Marc Champagne.
Thank you very much for your presentation and for your contribution to the business project. I know you have worked a lot regarding this issue, and you have answered to some questions we had regarding hazardous waste in commingled bin. So it's very interesting for us. I am the last, so I have no more question. Maybe one question. You tell us that you expect cost reduction. I'm sorry, I work in a private company, so I must talk about cost reduction. Yes, you expect cost reduction regarding thanks to RFID. It was a problem we discussed during the project, because for us RFID is very expensive. Because if you imagine to put RFID, it's exactly what you said. If you put RFID in a bottle, you have the price of RFID is not minus regarding the price of a bottle. So it's very big issue for us. So my question is quite the same. I already asked what other kind of solution we can imagine to reduce the price of this kind of approach.
We have already used a cheaper solution using the QR code, where very trivial objects which cost few cents that needs to be provided with some amount of data. So QR code is another good alternative that we had considered. And
do you imagine to have enough memory and you can store enough data?
If the object is very trivial, I don't think there will be a lot of things to describe with that object. So QR code would be sufficient to provide a minimal amount of data.
Okay. So if we consider again RFID, you explain in your document that RFID must improve. What are the most important improvements you imagine for RFID to be compliant with our problem?
There are several issues with RFID, of course. First is the memory for it. If it has a greater amount of memory, that will of course improve the approach. Secondly, the reading is also another problem that I said to one of the jury members, that we can't really read RFID tags if they are all assembled at one place. At one read we cannot do there. So there are misreads of RFID tags. Also the battery power, even if the memory is increased, the read time is limited by the time by which the reader powers the tag. So that is also an issue. Even if the memory increases by 10 times, the read time will be very limited, and it will be like a fraction of seconds during which it has to read the memory. So that reading algorithm or the reading approach should also improve for the technology.
This is what we have seen previously. Okay, just for my own comprehension of your work. For you, what are the main important issue you have treated in your document, and what are the most relevant improvement you have provide here for you? For the research, for example, it's not so often that research is interested in waste management, for example. So for you, what is the most
I would say that I'm happy that I have provided an approach that would enable Google not to have my data of what are the things I'm using. That's one of the good contributions, I would say, in this thesis. And considering the Internet of Things approach, if the trend goes for Google and Facebook, they will also be interested in tracking our everyday objects. So I'm happy that at least we can prevent them from getting some of our data, even if not all.
Thank you.
Michel Banat.
So, like my colleagues, I want to congratulate you for your thesis work.
Thank you.
And I have just a very small question related to the perspective of your job or your thesis. Could you precise what you mean by tools for building tangible objects?
Okay, so suppose we have these objects and we want to build a customized tangible data structure for this. I want to based on my requirement. I have already said that based on my requirements of application, I design the tangible data structure here. So if I have a new application to design, or if I have a custom requirements, so that would help me to decide what kind of tangible data structure I would build. It could be a mix of a linked list for some parts and then a tree in the other part and then merge them together. So it would be a kind of design tool that would have the intelligence to propose a data structure based on my requirements.
So today, how do you? What is today? What tools have you to build graph?
So if I have these objects, and if I also carry a chair with me when I'm moving, and this is a hypothetical, I don't have that solution yet. If I have all these objects with me, and I want both the feature that I want to detect the missing object as well as the assembly assistance. So maybe it would find me a solution that would build a graph for this type, and it would build a tree and then merge these two structures together to provide me this combined solution.
Okay.
Thank you. Paul.
So I won't ask you a question. I think we already discussed a lot during this 3 years. I want to thank you for the work, and I want to say that it was a pleasure. You were very positive and committed to the work. And I would also stress that it wasn't easy for you at the start, because this kind of unconventional approach made you work in a situation of uncharted territory where it wasn't obvious whether we would find a good solution or not. And so I want to thank you for the work and having
thank you too for providing me the opportunity.
Good solutions.
Okay, so I think I don't have many questions, except I want to come back to this composite objects.
Okay.
As far as I understand, your approach works well when the whole set of objects is known and the structure won't evolve over time.
No.
Meaning that if I want to add one personal item, it would be difficult to update the whole set of objects, to link them
if I
together.
want to maintain the consistency.
Yes.
Yeah, if it's like a completely connected graph, it would be easy. If it's a k-connected graph, it might be easy to, it might be easy to add a new object based on the graph, basically.
Mm-hmm. Yeah.
If I have a tree structure, I can easily append it in the bottom and then add it.
Mm-hmm.
If it's a completely connected graph, then I maybe need to restructure the entire graph and
to
rewrite few
update,
tags.
So it's not really meant for dynamic sets of objects, or
yeah, if it changes very frequently every hour or something, it will be difficult.
Mm-hmm.
The approach is more static if it changes lesser frequently.
Okay, yeah. But you presented a number of potential use cases with static sets.
Thank you.
Okay, and just the last question. In fact, you gave some qualitative comparison between your approach and the approach with an external infrastructure, and so tangible data against. But it's mostly qualitative, and I expected some more quantitative comparison, maybe in terms of user experience. Would this change anything in terms of user experience? How much time I need to wait until one of the bins is going to open? I have an object, a waste item. I believe that I have 3 bins, and one of them will open at depending on what kind of waste I have to deliver. And so, would it change anything about the time I have to wait until I know where to put my item to have an external infrastructure, or for me as a user, I won't notice anything if I use your approach instead? Local approach.
In the autonomous approach, yeah, it's not very time-taking process.
Mm-hmm.
Once it reads the tag, it's again based on the technology, RFID technology.
Yeah.
So once it reads the tag, the computation is done within a second probably.
Okay.
It's not a very time-taking process for the computation.
Yeah. And if you use an external infrastructure, would it be longer?
It would be obviously longer. We need to send the data, do the computation. There will be an additional overhead on the transmission time, of course.
And maybe the bin would never open due to a failure somewhere. Yeah. Okay. And I understand the incentives for Veolia or actors like this to deploy such a system, and for the user. Will they be happy with this system? Did you talk during the ANR project with users to know how well they would accept such a system?
Yeah, the user experience is. We really didn't go and ask the users, but of course, maybe initially they have to make an effort to comply to this new ways of dealing with the waste.
Mm-hmm.
But of course, we get used to newer ways, and it will be like a daily affair, and it won't be a problem.
Okay.
And the pervasive applications are meant to be user friendly, so it shouldn't be a problem.
Okay. So thank you.
Thank you.